Welcome to NGSS Physics. We're going to learn how to calculate energy today by using a couple of formulas. What you'll need today is a pencil, a calculator, and your formula sheet, maybe a piece of scratch paper. So if you don't have any of those things, pause it right now and grab those things so that you can do some of the calculations with us today. If you've got everything, let's go ahead and get started. I want to remind you of the two different types of energy, kinetic energy and potential energy. Both of these energies, kinetic energy is energy of motion, and potential energy, stored energy, where you have some formulas that you can find on your formula sheet. So find your formula sheet right now and take a look at the motion side of your formula sheet. Right above that is the force and energy section. In the middle column, you're going to find the formulas that we're going to use today. Let's start with kinetic energy. Kinetic energy, the energy of motion, I said in the previous lesson, depends on two factors, the mass and the velocity. They're both directly related to the kinetic energy. If you increase either of those, you increase the kinetic energy. Take a look at the formula, okay, that we can get based on those parameters. The kinetic energy is equal to 1/2 times the mass times velocity squared. The question is, what has the greater effect on kinetic energy, mass or velocity, and why? By analyzing the formula, it's very easy to see what the answer is. Definitely, the velocity has a bigger effect on the kinetic energy. If you increase the mass by a factor of 2, it would only increase the kinetic energy by a factor of 2, as opposed to the velocity. If you increase that by a factor of 2, that would quadruple the kinetic energy. So velocity has a much bigger effect when you change that on the kinetic energy. Let's take a look at the units for kinetic energy. The units of kinetic energy are going to be called the joule, after James Prescott Joule, scientist that actually discovered the relationship between heat energy and mechanical work. This led us to the law of conservation of energy. Just like the Newton, the joule is a made up unit derived from the units that are measured to use in the calculation, which means mass and velocity. So if we take a look at the formula, Ke is equal to 1/2 the mass times velocity, and we insert our units, kilograms for mass, meters per second for velocity, but of course there are two of them, we get kilograms meters squared second squared. Kilograms meters squared second squared is called a joule. It's very similar to the Newton. Remember, the Newton was kilograms meters over second squared. But if you have that meter squared on top, it's now a unit of energy called the joule. I'm going to write that formula off to the side a little bit so that you can see it a little bit easier. Sometimes we don't really want to solve for kinetic energy. We might want to solve for the mass or the velocity. In this case, the formula could be manipulated so that the velocity is equal to the square root of 2 times Ke over m. Or if you're solving for the mass, it's equal to 2Ke divided by v squared. That's not v times 2, that's v raised to the second power. If you have a hard time manipulating formulas, you might want to add it to your formula sheet right by the kinetic energy formula in the middle column of the force and energy section. Potential energy. This is stored energy, and there are all kinds of different formulas for potential energy. We're going to focus on gravitational potential energy. Gravitational potential energy really depends on three things: the distance between the two objects, and in this case, the height above the Earth, the mass of the object in question, and the gravitational pull on the object. For here on Earth, the gravitational pull, okay, is always going to be the same number, and you already know what that number is. Let's see if you can remember it before we get there. The higher the object, the more potential energy we're going to see. The larger the mass of the object, the more potential energy that we're going to see. The higher the gravitational pull, the more potential energy. Of course, like I said before, here on Earth, the gravitational pull is going to be the same for every object because Earth has only one one constant g associated with it. We're going to use this formula then to solve for potential energy. And once again, remember, this is gravitational potential energy. M stands for mass, G is that universal constant, the acceleration due to gravity, and h is the height. Now, if we weren't on Earth, then this G would be a different number. But if you didn't remember it, remember that 9.8 meters per second squared? That's what I mean by G. All right, so what are the units for potential energy? Well, it's energy. So the same units are going to apply. It's going to be a joule. But remember, we said the joule was a kilogram meters squared second squared. That's not going to change. The joule is kilograms meters squared second squared. Let's break this down into our formula to see where these units come from. The mass is where we get the kilograms. That gravity constant, meters per second squared, is where we get one of the meters and the second squared on the bottom. And then the height above the ground is where we get the other meters. So you can see that it's exactly the same units as what we had for kinetic energy. And just like kinetic energy, we don't have to solve for kinetic energy with this formula. We could solve for mass or even height by manipulating the equation around. So once again, using that formula, we can solve for mass, which is the potential energy, divided by GH, or we can solve for the height if we use potential energy divided by mg. All right, let's take a look at some sample problems. Let's say you're serving a volleyball with a mass of 2.1 kilograms, and the ball leaves your hand with a speed of 30 meters per second. The ball has what kind of energy? Now calculate it. You can't really calculate the energy unless you know which energy you're talking about. And it looks like the ball is in motion. So with the ball in motion, we are really talking about kinetic energy. And so I need to find the kinetic energy equation. All right, there it is, 1/2 mv squared. Now I need to find my mass. Well, here is 2.1 kilograms. Kilograms is a mass. I need to find my velocity. 30 ms, m over s, meters per second, is a velocity. So I need to plug those numbers in, just like that. And I get my calculator out, and I get an answer of 945. Let's look at another problem. A baby carriage sitting at the top of a hill, 21 meters high. The carriage with the baby weighs 1.5 kilograms. What kind of energy does this one have? Well, the carriage is sitting there, it's not moving, and it's at the top of the hill. I'm going to say this has some potential energy. Okay? It's not moving. And I've got some numbers there. Kilograms tells me that this is a mass. Meters high, well, that's going to be my height. So what do I need? I need my formula for potential energy. You know what? I've got the M, I've got the H, but what about the G? Remember, anywhere on Earth, G is a constant, okay? It's 9.8 meters per second squared. So keep that in mind. That's not going to be given in the equations. That is a constant that should be known. It's at the bottom of your formula sheet. Plug all those numbers in. Mass, G, and H. Calculate it out, and you get 308.7 joules. Okay, sample number 3. A car is traveling with a velocity of 40 meters per second and has a mass of 1120 kilograms. The car has what kind of energy? Calculate it. Okay, looks like it's in motion. So in motion, I'm going to say it has kinetic energy. Okay, kinetic energy, that's what I have. I find my formula. I got to figure out ms. Well, that is velocity. kgs, that is mass. Plug those numbers in, get my calculator out, and I get 896,000 joules. Now, sometimes when we have very big numbers like this, we like to convert things, okay, and get rid of the zero. So if I move my zeros 3 spots, I can convert this to 896 kilojoules, okay, moving my decimal point. Girl sitting on a platform 20 meters high. Aha, this looks like a height. This looks like a mass. She's not really moving, and I know her feet's moving in that picture, but really we're going to be calculating her potential energy. Using the formula, I don't know what G is. Aha, remember it's that constant, 9.8. Plug the numbers in. Crunch the numbers on your calculator, 1,744.4 joules. Again, 1.7 kilojoules if you convert it. All right, I've got two problems for you here. Two objects lifted by a machine. One object has a mass. Okay, this mass you can use in both of those equations, and it's being lifted with a speed. So you can then calculate some kinetic energy. Okay, the other has a mass, and it has a rate of being lifted, a speed. Okay, so it's obvious that we can use those numbers to calculate the kinetic energy for both. And then B, which object has more potential energy when it's lifted to 10 meters? Aha. What would we need there? Well, you need to pull out both of those equations to do both of these questions. And here's the solution. Okay, object 1. If we plug in the numbers, 2 kilograms, 2 meters per second, we have 4 joules. Okay, that's the kinetic energy. Now, the second one was being lifted with a much bigger speed and a much bigger mass. So, of course, it's going to have a lot more kinetic energy, 18 joules. The second part of the question. Now, this one's a little bit easier, okay? Now that we have mgh, we know that g is the same for both of these objects on either side. Both of them are being lifted to the same exact height, 10 meters. So it really depends on the mass. The one with the bigger mass is obviously going to have the bigger potential energy. Okay, a train traveling down the track with some energy. And has a velocity of 10 meters per second. Can we calculate the mass? Now, this is a situation in which we need to manipulate a formula. Because the train is in motion, I'm going to use the formula for kinetic energy. And because it's asking me to solve for mass, I'm going to manipulate the formula to solve for mass by timesing by 2 on each side and dividing by b squared. And I get a formula that looks like this. Now it's very easy for me to plug in my energy units and my velocity, just like that. Crunch the numbers, and I get 114 kilograms. All right, paper airplane with a mass of 0.5 kilograms is flying with a kinetic energy of 550. Okay, big clue. Since it has kinetic energy, I'm going to use the kinetic energy formula. This time I'm being asked to solve for the velocity. So I need to manipulate the equation around. Times 2 on each side, divided by m, and then square root each side. And I will get a formula that looks like this. Okay, my Ke, is given in the equation. My mass is given in the equation. All I need to do is plug those numbers in. Make sure you use your square root sign correctly, and you should get the answer of 46.9 meters per second. Oops. A 5 kilogram trophy with 3,500 joules of potential energy is sitting atop stairs. Calculate the height of the stairs. All right, so it's got potential energy. So this time I want to use my potential energy formula. But they're not asking for potential energy. They actually gave it to me in the question. What they're asking for is height. So I want to divide out by mg on each side, and I get an equation that looks like that. Plug some numbers in. Remember, g is 9.8. That's a constant. 71.4 meters. All right, so here we've got a final question, not necessarily a calculation, just an idea of that conservation of energy again. As the kinetic energy increases, the potential energy will decrease and vice versa. So if we're looking at this basketball, which ball shows the greatest potential energy Which one will show the greatest kinetic energy? Well, way here, the highest height will give us our best potential energy. And all of that potential energy is changed into kinetic energy way down here at the bottom. So that's where we get our maximum kinetic energy. In summary, kinetic energy can be calculated using the formula Ke is equal to 1/2 mv squared. Potential energy can be calculated using the formula Pe is equal to mgh. Remember, here on Earth, that g is a constant, 9.8 meters per second squared. Thanks for listening. I will see you back in the regular classroom.